Going to the last day of the mini courses, and we will start with João Paulo, who will continue discussing regular foliations on surface.
Okay, good morning. Can everyone hear me? Hear me well? Okay. So I will finish the mini course which was started by Carolina. And let me just begin by reminding what Carolina did in the last 2 classes. The goal was to classify regular foliations on surface. And as you saw in the last classes, we do this by considering the Henrique's classification of surfaces and considering each case in the list, which is given by the Kodaira dimension of the surface. So in the last class, Carolina classified the case of Kodaira dimension minus infinity. And the remaining cases are the Kodaira dimension 0, Kodaira dimension 1, and Kodaira dimension 2. It turns out that for cases Kodaira dimension 0 and 1, the classification goes in a more or less similar way of the case Kodaira dimension minus infinity. In all these cases, we will be able to find a foliation on the surface with which we can compare our original regular foliation and give some and get some information on the foliation. Okay, so on all these cases, we can find a foliation, a nice foliation on S, with which we can compare our original regular foliation. Okay? So the proof goes more or less in a similar idea for all these cases. And today I want to talk about the last case, which are the surfaces of general type. So surfaces with maximal Kodaira dimension. What's going to happen is that we cannot, in general, find nice foliations on these surfaces for which we can apply the same methods. So in this case, we cannot, in general, find nice foliations on S. So as we are following Brunella's paper, the proof of his result, as stated by Carolina in the first class, will go in a different way. So for this, let me give an example of a regular foliation on a surface of general type. So let's consider the bi-disc in C2 and consider a lattice inside the automorphism group of the bi-disc. I'm just call this D2 to be easier. So consider a lattice which is co-compact. And let us consider the portion of D2 by this lattice. This will be a surface of general type. Right? And as you can see, looking only at the bi-disc, we have two natural foliations which are given by the projections. So there are two projections which give two foliations on S. So let's call them F and G. Okay?
For that, you have to take the gamma contained in the automorphism of D to the square, right? There is an automorphism that exchanges the factors. So
sorry, I didn't.
You have to take gamma contained in automorphisms of D to the square.
Yeah, that's.
No, there you can interchange the factors, right?
You mean this?
No, in automorphisms of D times D,
yeah,
there is a map that sends F to G and G to F.
Yes.
So in the quotient, you don't have two foliations, you have a two web.
Yeah, you're right. So let's just assume this lattice is as nice as possible. So we have two foliation. Okay. So we have two possibilities here. The first possibility is if this lattice is a product of two groups, subgroups of the automorphism group of D, then in this case, these two foliations will have compact leaves. And more generally, gamma can even be finite index. Gamma can even have, this happens even if gamma has a finite index subgroup, which is a product. camera is here, right? On the other hand, if gamma does not satisfy this condition, it will turn out that the leaves of F and G are dense leaves on S. Okay. And it's possible to prove that considering this S, these are the only regular foliations on S. I will not do this here. Okay, so this is more or less an idea. And our ultimate goal is to classify regular foliations on any surface of general type. And one strategy is to see what properties this example gives and try first to see if you can prove that all regular foliations on any surface of general type also satisfy these properties. So we see here in this example that there are only two possibilities: either a regular foliation is a fibration or a foliation with dense leaves. And noticing that there are two foliations with the same property, which are transverse, we also have more information here. We see that these two foliations are transversely, have a kind of transverse structure. And in this case, it turns out that this structure is a transverse hyperbolic structure. So let me remind you what these structures are. These foliations are transversely hyperbolic. So let me just remind you what this means. So let me give a very general definition. Let's just consider a manifold. Doesn't even have to be complex, a real manifold. And F, foliation, regular foliation. Of codimension Q. So by definition, this foliation is given by a family UI Fi where the UI are open subsets of M, which cover the manifold, and Fi are submersions onto their image. Okay? So in this case, the plaques or plaques, I don't know. It's plaques, right? Plaques are given by the pre-images of Fi, connected components of the pre-images. And moreover, if UI intersection Uj is not empty, then there exists Gij from Fi UI intersection J to Fj UI intersection of Uj, local diffeomorphisms such that Fj is Gij Fj. So it's easier to see the picture. We have UI, you have Uj, this goes to RQ, this goes to RQ, and in the intersection we have Gij. Okay? And this set gamma of the Gij's is a set of local diffeomorphisms, is a pseudo group, and we call this the transverse structure of F. Okay? So, if these maps have a nice way, if they are nicely described, we say that this foliation has this nice structure, transverse structure. But let me be more precise. So, if now, if N is a homogeneous space where G is a Lie group and H is a closed Lie group, and we ask that the Fi take values in N and the Gij are local diffeomorphisms of N. In other words, they are elements of G. Then we say that F is transversally homogeneous with this structure. So all this is to consider. I'm doing this to say that in our example, the example I gave before, the foliations have this kind of structure. So let me remind you the foliations. So the foliations are given by the projection. You consider the projections and push it down to this surface. And since the foliations above are the projections, here the disk, we can see it as H2, hyperbolic space. And this is a homogeneous space. Let me remind you which groups. Does anyone remember the groups here? It's SO plus 1. There are some Lie groups here. I'm not going into details. And it turns out that F and G are transversely hyperbolic. Okay? So Brunella's theorem says exactly that. All foliations satisfy these properties which are given in the example. All foliations on surface of general type. So suppose S is a surface of general type, F a regular foliation on S, then either F is a fibration or F is transversely hyperbolic with dense leaves. Okay, is it clear? The statement? So unlike the other cases which are given by Carolina, we don't actually have an explicit description of foliations on surfaces of general type. Until this moment, we only have this. And of course, it's an open problem to classify, to give an explicit description of surfaces, of foliations on surfaces of general type. Okay. So let me more or less give an idea how Brunella proves this. The proof is very different from the method of proof for the other cases. As I mentioned in the beginning. And okay. Okay, so one nice property of foliations, of transversally foliations transversally homogeneous foliations is that they have a developing map. So, transversally homogeneous foliations have a development which is given as follows. So let me just say it's G by H. So we have a Galois covering. P to the manifold. We have a group homomorphism from the fundamental group of M to G. And we have a submersion of P into the space, the homogeneous space, such that if you pull back the foliation from M to P, the resulting foliation on P will be given by this submersion. One nice corollary is that these foliations on manifolds which are simply connected are always given by submersions. Okay, because this will be the identity. So how does Brunella prove this theorem? So he needs to show that if F is not a vibration, then F is transversely hyperbolic with dense sleeves. And how does one show that F is transversely hyperbolic? So his idea was the following. So he proves two lemmas. The first one, which was also done by Carolina, is to show that S has to be a minimal surface. I'll not do it here, don't have time. And the second one, after showing this, he shows that the conormal bundle of the foliation is a pseudo-effective line bundle. Let me be more precise. What does it mean? We all know what effective line bundles are. And a pseudo-effective is, if you consider the numerical class, it means that if it is pseudo-effective, it means that the numerical class is a limit of classes from effective line bundles. L is, let me abbreviate this to PSEF. Is PSEF if C1L is the limit of C1 Ln, where Ln are effective line bundles. Okay? And this will be a nice property because of a result by Demailly, which says the following. This is from the 90s, I think. I'm not sure. If on any complex manifold, if L is a Psef line bundle, I think I can erase it. Then there exists a singular Hermitian metric on L, which moreover has a non-negative curvature. And what is a singular Hermitian metric? It's just a metric, natural Hermitian metric, multiplied by the factor e to minus f, where f, this is local, right? Is a blurry subharmonic function. And this is singular because f can have poles, and in the places where it has poles, this will no longer be a metric, a natural, normal metric. Okay? So we apply this to the pseudo-effective line, to the conormal of the foliation, and we find a metric on the conormal. And if you have a metric on a line bundle, we can dualize and find a metric on its dual. So we can find a metric on the normal bundle of the foliation, which has positive, negative curvature, non-positive curvature. So we find a metric. So just for the sake of exposition, let me suppose, of course, in Brunella's paper, he takes care, the main difficulty is taking care of the singular part, but let me just suppose that it's a metric just for the exposition. So we find a metric on NF with non-positive curvature. So geometrically, it's saying that if we take the foliation, we can find a metric in the transverse direction of the foliation with negative curvature. So more or less, we can already see that in the transverse direction, there's something with negative curvature, which will turn out to be hyperbolic. Okay, more or less the idea. So in this case of a real, of a metric, Riemannian metric, we have, we can conclude that F is transversely Riemannian. That's the Riemannian, or just Riemannian. It's a Riemannian. That's the correct way.
There is a subtle point that you must do metric is invariant by the Luminy.
Ah, yeah. I forgot. Sorry. I skipped a step. I forgot one step, which is important. An important step. Let me call this metric G. So we can extend this metric to the whole TS because we have a projection here. Yeah. And we are able to extend it to the whole surface. And this will be a metric. We can extend this metric to the whole surface, right? But the important step here is to show that this metric is invariant by the holonomy of the foliation Okay, I will not do this, but Brunella shows this. This will be only a local computation on the local description, right? No?
It's global information. It's integration by parts.
Global. But he uses the local description to prove this. Yeah.
Local is false. Local you can construct metrics with negative probability that are not conserved.
Yeah, it's global, yeah. But to prove it, yeah,
What is the question?
So he was saying that the argument is local, but it has to have a global component because otherwise you can produce a transverse metric with negative curvature, which are not invariant by the holonomy. Locally, it's easy to do that. So you have to do integration by parts to prove that it is invariant by the holonomy. And you need a global argument.
Okay. Any other questions? Oh, all right. I have 12 minutes. So this will using this, we will have that F is transversely Riemannian. So let me again just remind what this means. So just remember, before I told you what's the transverse structure of the foliation. So considering a foliation codimension Q, if you take the submersions to a Riemannian manifold such that the Gij are local isometries. So if this is satisfied in the definition of the foliation, then we say that F is transversely Riemannian or just a Riemannian foliation. So there's a lot of studies on Riemannian foliations. There's a book by Molino, called Riemannian Foliations, and we are going to use some of his results on this kind of foliations. So we are going to use Molyneux's results on Riemann foliations and one important result is a structure result, structure theorem, which says the following: if M is a manifold F Riemann foliation on M, then M is the disjoint union of minimals for F. And what is a minimal? Is a closed sub. Yeah, minimal set. I just abbreviated. Because he calls just in the paper, he just called minimals. He doesn't say minimal sets. And what is a minimal for the foliation? Is a closed subset which is saturated by the foliation. Which means if you take any point and the leaf going through this point, the leaf is contained in this set. And which is minimal with this property. Okay, so a minimal set is a set saturated by F, minimal with this property. Yeah. So in our case, we have a four-dimensional manifold. So let me just consider the real dimension now with a codimension 2 foliation. So there are only three possibilities for minimal sets. Either a minimal set is a closed leaf, a compact leaf, or a three-dimensional manifold, a hypersurface of the manifold, or a four-dimensional manifold, which is the whole manifold. Three possibilities. Let me call a minimal set M. So a closed leaf hypersurface oh, I have 6 minutes. Or everything. In this case, when it's everything, the foliation will have dense leaves, right? So where am I? So let's consider all these cases. Actually, I'm also using a finer description of this structure theorem, which can be found in Molino's book. Of all these cases, a finer description. In our case, we'll say that the following possibilities happen. We have 4 possibilities. So one possibility is that there's only one minimal set. In this case, the leaves are dense. We want to show this if the foliation is not a vibration. And moreover, by Molino's result, in this case, F is transversely Euclidean. In which case the n, over which we have the sublimations, is R2, or elliptic. In this case, it's S2, or hyperbolic, which is the case we want to show, AD2. Okay, so this is one possibility, and we have other 3 which will roll out. The second, leaves are compact. We suppose this does not happen. All leaves are compact. So we can already rule this out by supposition. All the minimal sets are real hypersurface. And we will also rule this out because in this case, he also shows that the minimal sets give a vibration over S1. And this cannot happen because S is a surface of general type. If you have a vibration over S1, the Euler characteristic will be 0. It's a contradiction. For surface of general type, this is always positive. Okay? In the 4th case, two leaves are compact, and all the others are real hypersurface, which give a vibration. But I only say here that by topological considerations, it's possible to show that in this case, these leaves are S2, are a sphere. And as you can remember by Carolina's last class, if we have a sphere which is a leaf, all the leaves are spheres, and we have a vibration by spheres. And this cannot happen too because we are on a surface of general type.
So what kind of input you are using to leaves or the student? So I'm asking what kind of information he's using.
It's something like this. I'm not, I don't know exactly the details. Brunella only says that if you have a vibration by real hypersurfaces, and he says the ends are these two compact leaves. In this case of surface of general type, these two ends have to be spheres. But I don't know the details exactly.
I think it's the same thing, yeah. It's just the fact that the topological Euler characteristic is positive.
Yeah, probably something like this. Okay, so this is also ruled out, and we have this case. So since my time is over, let me just say that now we concluded that the leaves are dense, and F is transversely Euclidean, elliptic, or hyperbolic. So why it has to be hyperbolic? Because remember, we have a transverse metric with negative curvature, and we can more or less push forward this metric to the base. And so the base will be a curve, a complex curve. In this case, it's C or P1 or D. And this metric will descend out to the base. Since it has negative curvature, the only possibility is that it's the disk. So the foliation is transversely hyperbolic, and this is what I wanted to show. Thank you for your attention.
Thank you very much, John. Questions, comments?
In your example of a product of two disks, can
Yeah.
you write, is it possible to write down the metric?
Yeah,
Explicitly?
it's possible to explicitly show the metric. It's the Poincaré metric on the disk, I think. Yeah, Brunella has more results on this, which gives a more nice description. This is only an idea in Brunella's paper. Actually, all this is not true, what I said, because the metric is not a real metric. It has singularities. And Brunella's work was to show that these arguments still work in that case, using results by, let me see, by Kellum, which generalize this transversely Riemannian scenario to what he calls uniformly quasi-isometric foliations. And Brunella's work is to show that these foliations are uniformly quasi-isometric, which is some kind of generalization of transversely Riemannian foliations.
I have a quick question. So the fourth case, it's only two leaves are compacted.
Yeah, only two
Exactly
leaves.
two.
Only two leaves. This you can find in Molino's book, but I found via an middle term, which is Gobion's book. It's a book on real foliations called Feuilletage.
Any other questions from here? Frank, do you have questions?
Are there any questions?
I have a question. When you say transversely homogeneous foliations,
Yes.
is there some connection between the leaves and the group and this action? I didn't get it well.
Yeah, the group give, you remember the GIJ, which give the transverse structure. So these GIJs will be elements of the group G.
But is there something you can tell about something geometric that we can tell about the foliation, like because there is this transversely, this idea, what it means?
Yeah. Yeah, we say something about the transverse structure, but I don't know if, in general, what it says about the leaves itself. We saw one example here, but in general, I don't know.
Thank you.
A question, yes, so do we expect that the foliation is the quotient of a B-disc in that case?
Yeah, Brunella says that. He says maybe all foliations are given
So,
like the example which I gave in the beginning.
so for
But,
instance, if we have a second foliation, are we able to prove this?
Yeah, this is true. If we are able to find a second foliation, then we can prove that the foliation is given by the quotient of by disk. But in general, I don't know. I don't know how to find a second foliation. I think Brunella gave some conditions in other papers, but I don't remember which one they are.
Okay. Thank you very much.
Thank you.
Okay, I think we can thank João again. And resume in 5 minutes, no?
Yes.